We are now going to move on to the topic of nonlinear regression. We want to figure out what techniques we can use to find the best fit curve for a set of data where it looks like the data doesn't necessarily have a linear relationship between the two variables. A good example and relevant example of this is the number of infected people with the coronavirus in California in the month of March. So what I've done is I've given you the data for the days in March and the number of infected people on that day every other day, because that way I could fit all the data onto this worksheet more easily. So for example, on March 2nd, there are 15 infected people, or there were, okay, but now on March 28th, there are 5,151 infected people. And what I've done is I've plotted that data to the right. And you'll notice it seems like the data is growing exponentially. So the question is how do we know that the data is growing exponentially? I've plotted the data using Excel, and Excel has given me an exponential fit, but how do we know that fit is appropriate? Okay, so the question that we're going to answer here is what type of relationship exists between the infected population I and time t. I believe that relationship is exponential. And so if that's the case, then I of t is going to equal a constant times e to the rt. Now, how do I know that is the best fit? Well, I'm going to consider something that is called a semilog plot. A semilog plot is a plot of the natural log of the dependent variable, in this case I. So we're going to plot natural log of I versus t. So now we have a semilog plot that I've shown here, and it appears that data is linear. It appears that we can fit that data using a linear regression, that there's a linear relationship between the natural log of the number of infected people and time. Now, why is it that if you start with exponential data, that when you take the natural log of the dependent variable, that you get something that looks linear? Let's explore that for a second. Okay, so we're going to say that I is given by that exponential relationship. Then the natural log of I is the natural log of c e to the rt. And we know from properties of natural logs that that's the natural log of c plus the natural log of e to the rt. And so we can write that as the natural log of c plus r times t. And so what we see is that there is a linear relationship between natural log of I and t. In fact, we can think about this as being our beta 0, and then r as being our beta 1. Okay, so that explains why when we looked at the semilog plot that it looked like it could be fit with the best fit line. In fact, we saw the coefficient of determination for that fit is 0.9836, very close to 1. Okay, so this gives us a strategy for trying to figure out the best fit exponential function. The first thing to do is to find the semilog plot and then find the linear regression for that set of data, the natural log of infected versus time. Now, once we have that fit, how can we find the corresponding exponential fit? So what we're going to do is let's assume that we ran natural log of I of t, okay, against t, and then we got our regression. Our regression is going to be beta 0 hat plus beta 1 hat times t. We can then turn that back into an exponential function. So we can do e to the natural log I of t is going to be e to the beta 0 plus beta 1 t, and we can write that, of course, as e to the beta 0 times e to the beta 1 t. That tells us that the number of infected people, I of t, is really a constant times e to the beta 1 hat t, where that constant is e to the beta 0 hat. Now, that gives us a way to start with the regression and then turn it into the best fit exponential function. What does that mean for our data? Well, what is I of t? Okay, well, it's going to be e to the beta 0 hat. So I'm going to look over here at our regression that it gives us. There's beta 0 hat, there's beta 1. Okay, so I'm going to plug those values in. That's going to give me e to the 2.5543. That's our constant. And then e to the 0.2192 times t. Okay, so e to the 2.55 is about 12.86. E to the 0.2192 times t. And now we have our best fit exponential function. In fact, I believe that if we look right here, that yes, we did get 12.86 e to the 0.2192 times t. Okay, that's helpful because now we have the best fit exponential function, but can we understand what it means? Okay, so let's see, let's do, this is 12.86, and then e to a number times t, we can think about it as e to that number to the t power. It's another way to look at it. Okay, so this is 12.86 times 1.245 to the t power. That's what e to the 0.2192 is. And that gives us some interesting information. That says that the number of infected people in California is increasing at 24.5% per day. And that is our first technique for nonlinear regression, using semi-log plots to find the best fit exponential function.